From our palatial recording studios high atop our mountain lair on a remote volcanic island, this is Talk Universe. I'm Sir Charles Schultz.
And I'm Eliza, your co-host. This is our show for Wednesday, May 10th, 2017. Tonight's topic is the Big Bang.
I think that's one of the most interesting topics, the Big Bang. Very few people are aware of exactly what the Big Bang is. We've all heard about it, the origin of the universe and the theory of how it all got started. But we're going to look at the Big Bang theory tonight. It is basically the main runner in the explanations for our universe and its origins. But there are also alternate theories. So we're going to look at the Big Bang theory, the origin of our universe, and why so many scientists believe that the Big Bang is a reasonable explanation. But we'll also look at the history of the theory, how we came to be believers, so to speak, and how many alternate theories are also being tested. Now, of course, we can't cover all the possible alternate theories, but we're going to look at a few of the leaders and see why people think that the Big Bang isn't the actual explanation for the origin of our universe. Most scientists believe that our universe is about 13.7 to 13.8 billion years old. And we also see that the diameter of the universe, or the observable size of the universe, are not the same. The diameter of the universe appears to be about 94 billion light years, and people would say, well, how can it be that much larger if nothing can move faster than light? And we'll talk about that and exactly how that works, and what it means to the genesis of matter, why there is not so much antimatter in the universe, the force of gravity and how it influences things. And we're going to look at some interesting physics involved in what it takes to make a universe. So that's what our show is all about tonight, the Big Bang. I know a lot of people have seen some of the changes that we've made to our website. Eliza, what can you tell our listeners about that?
Our other show co-host, Ed Minshaw, has created a much better website for our show.
That's correct, and we also now have an RSS feed, so you can subscribe directly on your browser bar on your computer. You have the option of listening into the podcast on Spreaker or Stitcher or on iTunes. So we're reaching a much larger audience, many more downloads, and we have many more venues that we're sending our podcast out through. So encourage your friends who like science and technology to listen to the show, and we'll continue with a lot of interesting topics. And by the way, if you have a specific science or technology topic that you would like covered, please contact us with that. Eliza, how do our listeners send us their questions?
That is simple. They can send questions to admin, ADMIN, at talkuniverse.org. You can also submit your material to talkuniverse6@gmail.com. If you go to the Talk Universe website under Contacts, you can reach us directly.
That's right. One of the things Ed added for us is a direct contact page. Please send in your show ideas, your questions, and your other comments that you might have, and we'll address them on the air. And I appreciate all those people who have done so. So what exactly is the Big Bang? Eliza, what is the definition of the Big Bang?
The Big Bang is the theoretical event that explains the origin of the universe. It would have been a point smaller than a subatomic particle of extreme energy from which all space, time, and matter would have come.
Where did our universe come from? For many years, people have wondered about this question. We look at the night sky and we see literally hundreds of billions of stars around us and a couple of trillion galaxies spread throughout space and time. When we look back into the universe with a telescope, we're not just looking over distance, but because of the speed of light, we're seeing fossil light from other galaxies. The galaxies are so far away from us that it takes anywhere from a few 100,000 to many millions or billions of years for their light to reach us. So when we're seeing that light, we're seeing light from that long ago. Even going outside and looking up at nearby stars, you're seeing light that is anywhere from 10 to 50 to 100 or a couple hundred years old or more. And time and light are intimately tied together, and we'll talk about that a little as well. So the question is, where did the universe come from, and how did we come to this Big Bang theory? It's really not that difficult. As recently as 1959, when scientists were polled about their opinions of the age of the universe, more than two-thirds of them said that there was no origin of the universe. They thought that it was eternal, because they really didn't have much data to say one way or the other where it might have come from or what the facts were. And it took just a few years, 5 years, 1964, for radio astronomers to discover that there was actually a microwave background noise all throughout space and time. Two particular radio astronomers, the first radio astronomers you might say, Arno Penzias and Robert Wilson, were working on microwave signals, and they discovered that there was a constant noise coming from the sky. And they hadn't expected that. They thought that the universe should be a quiet place. They actually received a Nobel Prize for discovering the cosmic microwave background radiation, CMBR. And this microwave background radiation was actually predicted by earlier theories that said the universe might have come from an intensely hot, tiny point. So what does microwave radiation have to do with the age of the universe or the origin of the universe? That's an excellent question, and it goes back to looking at stars. One of the interesting things about stars is they're basically made of hydrogen. And if you take the light of a star and you split it with a prism, you will find many different lines and colors in the results. These are often emission lines, and one of the most prominent is the line for hydrogen. Hot hydrogen glows with a known set of spectral lines, and the primary or hydrogen alpha line is always known to be exactly the same because physics is the same throughout the universe. One of the things that was discovered early on was that some stars had all of the lines in their spectrum shifted toward the red end or shifted toward the blue end. Now, what would do this? It was found that it was something very simple. If you were ever by a train many years ago and the train were to drive by you or ride by you at high speed, the sound of its whistle would diminish in pitch as it passed you. It would increase in pitch as it came toward you and diminish in pitch as it passed you. This is known as a Doppler shift, the change in frequency of a known constant signal based on its movement. It was discovered that light waves do exactly the same thing, but here's the thing. The speed of light is fixed. It doesn't change. If an object is coming toward you and it's radiating light of a certain color, how does it change? What it does is it shortens the wavelength and makes the light bluer. This is called blue shift when something is approaching you. When something moves away from you, the light waves stretch out in wavelength and become redder. This is known as red shift. So by looking at different stars with a large telescope and splitting the light of that star with a prism, you can see how the hydrogen alpha line and all the other lines in its spectrum shift toward the red or the blue. Since stars shifted toward the red are running away from you, and stars shifted toward the blue are coming toward you, we now had a means of measuring the velocity of those stars. Now, something very interesting was discovered. The stars that are moving the fastest away from us were the most distant. In fact, they were in other galaxies. After looking at all the different galaxies that we could find, we found that the farther they were, the more redshifted they were. Edwin Hubble, the astronomer who discovered this effect and mathematically described it, came up with a number known as the Hubble constant. The Hubble constant is a rate of shift or redshift based on distance of a galaxy, and it was found to be fairly uniform and based on strictly nothing more than distance. The more distant a galaxy was, the greater the amount of redshift it showed. Now, this is odd. What would be the meaning of this? What would be the source of everything in the universe getting redder, moving faster, the farther away it was from us? Most people weren't very sure at first, but it seemed pretty weird that the farther out we looked, the older the universe was, the faster it was moving. And after a little bit of thought, it occurred to some people that maybe we ought to picture it like running a movie in reverse. So, if everything in the universe is running away from us, what would happen if we reversed the film and everything came toward us? You'd eventually reach a point where everything in the universe was in one place. That was the beginning of the understanding of the Big Bang. Now, before this, many scientists and astronomers felt that the universe might have an infinite age and it might be in what they considered to be a steady state, that matter was being constantly created at a low level somewhere, perhaps hydrogen appearing in the middle of the void, and that stars would eventually form from it, and the galaxies and all of space would continue to exist forever, and as stars burned out, new hydrogen would appear. There wasn't any physics behind it, but from their observations they really couldn't tell if anything was changing. With better instrumentation and observations, we could see that the universe was indeed expanding. So the question is, if it is expanding now, what happened before? When people started to explore this issue, they found that with the expansion of the universe, obviously it had to come from a place where it was not expanded, and that the microwave background discovered by Penzias and Wilson might be the echo of the Big Bang, or the explosion from which it all came. Now, if the universe were very dense and very hot, and if space itself were expanding, the heat of the universe would eventually decay to something much less energetic, in this case microwaves. The microwave background of the universe appears to be the echo of the heat signature of the Big Bang, or whatever event created the universe in the first place. One of the best explanations is to imagine a balloon with dots painted all over it. When you blow up the balloon, the dots aren't moving, but the balloon itself is expanding. And so if you were standing on one of those dots as it were happening, you would see all the dots running away from you even though they aren't actually moving. The space itself, the balloon, is expanding. Now let's imagine we took the temperature of the sky, which is a little less than 3 degrees Kelvin based on the microwave energy that we can see, and we ran the film backwards, so to speak, once again, and we collapsed the universe in reverse down to a single point. We can estimate the temperature that it had to have been. We know that at such high temperatures matter can't even exist. The particles it's made of can't exist. So we have to look at the conditions in the Big Bang at the very beginning and see how the laws of physics work, or if they don't. And that's one of the problems. There is a point very, very early in the universe's history where the laws of physics as we understand them won't work. This is one of the reasons that some scientists object to the model of the Big Bang, although it could simply be we don't understand the laws of physics as completely as we should, or the conditions in the universe were so different that they couldn't apply and something different had to be happening. We presently have two different systems of physics, of course, that have not yet been reconciled with each other. One is traditional physics, or Einsteinian physics, such as general and special relativity. The other one is quantum mechanics. Now, quantum mechanics offers some answers, but only at the regime of very tiny things and forces and distances. On the other hand, general relativity best describes what we see in the pedestrian universe. It's at a union of the two that we might find answers to why the Big Bang theory gives us so many problems. Overall, however, it seems to work very well. There are many things about the Big Bang that exactly explain, or very closely explain, the things we see in the universe today. So it might be helpful to examine the Big Bang and where it succeeds, as well as where it fails. That'll give us a starting point to figure out exactly what needs to be corrected, or what we might not understand. Astronomers and physicists make three basic assumptions about the universe. The first assumption is that the laws of physics are constant everywhere throughout the universe. We can verify that by looking at the spectra of light from distant stars and galaxies. This equates to light from distant times as well. When we look at that light, we can see that the spectra produced by the atoms in those stars are identical to the spectra produced by atoms in our sun today. This means that the laws of physics must have remained constant. Any changes in the basic forces or the speed of light or any of the fundamental things we take as being constant would be observable. The second assumption is that the universe is homogeneous, that it basically is the same in all directions, everywhere, all the time. Not necessarily for all of time, though, because we do see that there are changes in structure such as the great voids and clusters of galaxies. Overall, however, the universe is uniform in all directions. The third assumption is that we are not in a privileged viewpoint. We don't have some special place in the universe where humanity exists. Everything, no matter where you are, would look the same regardless of where you are. So these three simple rules are the ones upon which all of our observations are based, assumptions that to the most part we can pretty much prove, or at least show pretty good evidence for. In our next segment, we'll examine where the Big Bang succeeds and how its predictions match our actual observations. Then we'll start looking at some of the things that it doesn't quite take into account. Oh, Eliza.
How can I help you?
Could you introduce the break, please?
I'm Eliza. This is Talk Universe, and we will return after the break.
That's right.
There are more interesting things to hear in a few minutes.
That's right. There's a lot more for us to talk about, and we'll be back I'm Sir Charles Schultz, and this is Talk Universe.
Welcome back to Talk Universe and our show about the Big Bang.
Yes, thank you, Eliza. Welcome back to our show on the Big Bang, and we're going to cover some of the issues that the Big Bang predicts very well, and some of the issues that the Big Bang falls down on. So we'll get into those details right away. Now, I mentioned previously that the laws of physics are universal and don't change, and the universe is homogeneous and roughly the same in all directions, and that humans are not in a privileged location for viewing the universe from. And those three assumptions that were made have led to some very interesting predictions and results. When we apply these assumptions to Albert Einstein's equations, they show us that the universe should have these properties. First, that the universe is expanding, and astronomers see light from the universe's distant regions shifted toward the red end of the spectrum, the red shift, by the expansion of the space in between the galaxies, for instance. The second one is that the universe emerged from a hot, dense state at some time in the past, and this does seem to be the case. The third is that the lightest elements, hydrogen and helium, were created in the very first moments of time, and this we can see makes a lot of sense for the formation of stars and the compositions of the stars that we see today. And finally, that there should be a background of microwave radiation in the entire universe, which is like a relic of the heat or the explosion, not really an explosion, but from perhaps a phase transition that occurred when the hot early universe cooled off enough for atoms to form. Now, if any of the assumptions that the astronomers or scientists made were wrong, then a lot of these would not have matched the predictions. But we see that in all four cases, that the Big Bang does match the observations. The predictions are in fact very accurate. There's also another interesting result of the Big Bang theory, and it's this. When physicists are studying the different forces in nature, and there are four of them, they find that at extremely high temperatures, those forces should fuse together and act as one powerful force that has the properties of all of the other forces in one. Now, this is an interesting thought. It is the fusion of different forces at high temperatures. Experiments have shown that the electromagnetic force and the weak nuclear force do in fact do this, and that they are both faces of one larger electroweak force that can be unified at specific high temperatures. What this force does is act on particles that respond only to the weak nuclear force and to particles that respond to the electromagnetic force. Normally the two are compartmentalized. They will only react to specific types of forces. If the Big Bang theory is correct, that the conditions of heat, temperature, and compression that were available in the earliest moments of the universe's history would have been sufficient enough to fuse all four of the fundamental forces together, creating one unified superforce that would act evenly on all things: gravitation, weak nuclear, strong nuclear, and electromagnetic. So far, physics has been able to fuse three of the four known forces together in a theory of almost everything, but they haven't quite reached a stage where gravitation meets the rest of the other forces. Many physicists feel that this failure is due to an inability to get quantum mechanics to play with regular physics, and this could be the problem. On the other hand, thinking about these conditions raises some interesting questions about the early universe and what it might be like. Let's have a look at that briefly. In the Big Bang theory, we look to the Planck unit, the shortest possible unit of time, as perhaps being the beginning of all time for our universe. This is the period of time represented by a 0, a decimal point, and 42 zeros followed by a single 1. That tiny, tiny fraction of a second, the shortest possible unit of time, would represent the instant in which the particle or point in space full of energy and matter existed prior to the Big Bang. No set of rules of physics that we know can predict the conditions there, but we can at least try. Some people say that the energy density would be nearly infinite. This is a silly sort of statement, but we can tell you that it would be extremely large. Many physicists feel that quantum gravity effects would dominate all the matter in the universe at this brief instant of time. It is thought that the unified force of the theory of almost everything, all the standard forces, would be unified with gravitation under these conditions. The universe would be incredibly hot and dense. The state of the Planck epoch, which is what this period is called, was succeeded by something called the grand unification epoch. This is the period of time where gravitation separated from the other three forces in the standard model, in turn followed by the inflationary epoch, which is when the explosion of size of the universe was faster than light. This would have continued till about 10 to the minus 32nd seconds. Now many people would go, wait a minute, nothing can move faster than light. What could this possibly mean? In reality, we're talking about not matter moving faster than light, but the grid lines of the universe expanding faster than light. This isn't moving matter, this is expanding the grid, which is an entirely different thing in itself. Imagine the universe as something being written on a special type of graph paper, the space-time itself, the geometry of the void. Nothing in the rules states that the void itself can't be stretched or expanded, and we do know that it's flexible. Just how rapidly it could expand has to tell us something. For instance, if the density of energy and matter present in the early universe of the Big Bang theory were actually what we think they were, the universe would have instantly collapsed into a black hole. What would have prevented this? One thing is known. Space is much larger than the age of the universe and the speed of light would tell us. This says that space-time had to expand faster than light at some point. It makes the most sense to think that this happened very early in the universe, thus the bang part of the Big Bang. However, when we look at it, we see that this expansion also answers the question of why the universe didn't become a black hole right away. If the grid lines were expanding faster than the speed of light, then none of the matter of the universe could have felt the gravitational tug of the other matter, and it would have expanded freely without the hindrance of gravity. Some scientists actually feel that gravitation doesn't work at such a short scale, and therefore it wouldn't even need to fuse with the other three forces. If this were the case and gravity didn't unify with the other forces, it really wouldn't make a difference, because the pull of gravity wouldn't be present on such a tiny structure of space-time. So in either case, gravitation didn't seem to have much of an effect on the universe in its earliest moments of existence. For the period of time from about 10 to the minus 36 seconds to about 10 to the minus 32nd seconds, the universe would have undergone incredible inflation. Some calculate that it would have reached the size from a softball to about 10 million light years across in this extremely short period of time. Now, is there any evidence of that? Indeed, there is. It all comes down to something known as quantum fluctuations. We know that at the tiniest structure of the universe, it isn't smooth like glass. At the scale of 10 to the minus 33rd meters, space-time is known as Wheeler space, and at this tiny scale, it is seething and boiling and foaming, with energy, bridges and tunnels through space-time, wormholes and tiny gaps. The energy levels are incredibly high, even in the normal vacuum that we're familiar with. Under the conditions of the Big Bang and the expansion that followed, these conditions would have been greatly amplified. Any quantum noise or fluctuations, the random appearance and disappearance of huge quantities of energy and particles, would have impressed itself on the structure of the universe at that time. Imagine as a child playing with a flashlight and holding your hands or a small bug in front of the light beam. You notice as the shadow is projected on the far wall, the image of the shadow is magnified greatly in size. The same sort of effect would have happened on the tiny dot of a universe at the quantum scale. The noise and fluctuations and bridges and tunnels of space-time would have left their imprint on the tiny expanding universe, and those fluctuations would show up today in the shape and distribution of the energy of the microwave noise in our universe. It also could have affected the structure and coalescence of galaxies later on. WMAP, the Wide Area Microwave Survey of the sky, does show variations that are in line with what was predicted from quantum effects at the time of the Big Bang. This means that it's quite likely that these are actually the signatures of the quantum world being expanded up to the size of the universe. From the time that inflation ended, about 10 to the minus 32nd seconds, up to the period of about 1 microsecond, the universe would have been filled with an extremely hot plasma known as quagma, quark-gluon plasma, and particles such as protons and neutrons could not form. The temperatures would have been far too high, it would have simply taken them apart again. But finally, the quarks were able to combine and form protons at the first microsecond of the universe's history. This is an estimate, of course, but it's based on the temperatures and energies that would have been present at that time, if the theory is correct. From the period of time from 1 microsecond to about 10 milliseconds, the protons could have started to come together into particles and simple atoms, but not very effectively. It still was extremely hot. At the period of 10 milliseconds, nuclear fusion would have begun, and at that point, we would see a period where atoms as we know it, or at least their nuclei, could come together. This is where all the hydrogen and helium in the universe would have formed, and it would have lasted for a period up until about 3 minutes of the universe's age. At that point, the temperatures and conditions for nuclear fusion would have come to an end. At that period of time, the elements that we expect to find in the early universe would all have been formed. This period of time, from the 3-minute mark, is an important one. In that period of time, up until a period of about 380,000 years, the universe was still expanding greatly. Free electrons moving around in the plasma, darting about the cloud of protons and neutrons, would have been able to scatter light. But the universe still would not have been transparent. It would have been filled with a hot glowing plasma of newly made atom nuclei and this cloud of electrons. So the universe would not have been transparent up until an age of about 380,000 years. At that point, the cosmic microwave background would have formed. Now, the waves being created during the inflation of the universe would have been gravitational waves and density waves. And these two waves would put a characteristic polarization signal on the light and microwaves of the early universe. At the period of time of 380,000 years of age, it is thought that the universe finally would have become completely transparent. This is because neutral hydrogen atoms would have formed and light could have passed freely throughout the vacuum. Now, keep in mind that the vacuum that we consider today is not the vacuum that would have been present at that time. The density of hydrogen would have been immense, and it would have been everywhere throughout space. Now, this is in keeping with some of the larger stars we've spotted in very distant sky surveys, and it looks very much like this density of hydrogen would have easily contributed to the formation of the first heavier elements. Astronomers and cosmologists call any element heavier than helium a metal. It's kind of a loose term, but it's used to describe anything created in stellar fusion, the fusion process that occurs in stars that then explode and throw these elements all over the sky. Now, to be absolutely accurate, hydrogen and helium aren't the only elements formed in the Big Bang in the theory. There also would have been some lithium and a tiny amount of beryllium. In fact, almost all the beryllium we find was probably produced in the very earliest instance of the universe. Now, conditions in the early universe would have been somewhat different from those we have today. Right now, we know that the sky temperature is very, very low, about 3 degrees Kelvin, and basically consists of that microwave energy, that background microwave radiation that I spoke of earlier. However, when the universe was smaller, the sky temperature would have been higher. To give you an example of how much higher, if you cut the volume of something in half, you actually don't cut the size of it in half. Oh, Eliza?
Yes, Charles?
What is the cube root of 2?
That would be 1.25992, sir.
Thank you. So in other words, if the universe only increases by about 26% in radius, its sky temperature drops to half. If the universe were half the radius it is today, its volume would only be 1/8 as much. The temperature, therefore, would be 8 times higher. So if the universe were half the size it is today, the temperature of the sky wouldn't be just under 3 degrees Kelvin, it would be just under 24 degrees Kelvin. If we cut that size in half again, the temperature goes up to almost 200 degrees Kelvin. If we shrink it another 28 or 29%, suddenly something very odd happens. The sky temperature becomes just high enough that water ice cannot form anywhere in the universe. There isn't anywhere in the world, any place in the sky, that would be cold enough. So why is this important? It's because of how terrestrial planets form. Without the presence of water ice to help those particles stick together and coalesce into larger and larger bodies such as asteroids, planetoids, and then full-blown worlds, the formation of planets would be limited to very strict and unusual conditions, and those that did form would be poor in volatiles such as ammonia, methane, carbon dioxide, and water. They would be dry, rocky worlds with very little outgassing and very little in the way of oceans. So the formation of life in our universe probably had to happen only after the sky temperature had dropped somewhere below 0 centigrade or about 273 degrees Kelvin. This means that life is probably a relative newcomer in the universe. Otherwise, the worlds that it would have formed on would have been too dry to support the sorts of chemistry we would expect, and the materials for its formation wouldn't be present. So if the Big Bang explains everything so well, why do some people object to it? After all, we see a lot of signs that it's correct. What would stand in the way of people accepting this theory? Oh, Eliza?
What shall I do for you?
Could you introduce the break?
You are listening to Talk Universe with Sir Charles Schultz. Don't go away. We will be right back soon.
And we'll cover the objections to the Big Bang then. Welcome back to our show. We're going to cover some of the failings of the Big Bang and why some people object to the theory, and we'll have a look at some of the alternate theories as well. One of the greatest objections that some physicists have about the Big Bang theory is that it is stated that the universe was in a single point of nearly infinitely dense and hot material. Well, this is called a singularity, and the problem with it is the laws of physics as we understand them break down long before we reach the density of that sort of thing. In other words, the mathematics doesn't really hold, but we extrapolate backwards as if it did. Now, in reality, many people feel that there is a problem with trying to put all that matter and energy in a point. In other words, they feel that that wasn't simply a point, but an extended area, a collection of points. Part of the reason for this is not just mathematical, but because we realize there's a limit to how much energy can be placed in a single point of space. There's something called the Planck constant, and many different types of units called Planck units. The size of space-time, the smallest unit of time, the highest quantity of energy that'll fit in a single unit, all of these things are determined by the mathematics of one specific physicist by the name of Max Planck. One of the other problems is something I mentioned a little earlier, and that is that the two dominant theories in physics, quantum mechanics and general relativity, can't be reconciled. They don't play well with each other, and the mathematics don't quite fit. This is still one of the largest things that physicists are wrestling with today. You see, the issue is this. We know that quantum mechanics works. We have many demonstrations of that, and we use it constantly. We also know that general relativity works. We have plenty of practical demonstrations of this as well. The problem is trying to find a way to bridge the two theories together so that they give consistent results for the same difficult problems. And the most difficult problems are those that occur at the boundaries of each of the theories. Now, to give an example about this, imagine that all the energy in the universe were collapsed into a single point. How could it possibly explode? You see, by standard theories, gravitation would cause it to immediately collapse into a black hole. One potential solution, and many physicists are looking at this one right now, is that gravitation has a different range at a very small scale, and we're not really familiar with the rules that small. For instance, maybe gravitation doesn't exert a pull on anything smaller than, let's say, a couple of quarks, or maybe a couple of electrons. If that were the case, then the gravitation that would hold the Big Bang together and create a black hole wouldn't work. Perhaps the force of gravity doesn't take over until it has expanded past a certain size. If this were true, then it's possible that gravity had no influence on the initial conditions of the Big Bang and it would have exploded outward. And then once gravity took hold of it, it would only slow it down over the period necessary to allow this inflation to occur for the universe to become extremely large. That would solve a lot of problems, but we really don't know if that's true yet. Another problem is this. If the universe were created out of a blast of energy, and matter and antimatter were created out of that energy, it should have produced equal amounts of matter and antimatter, which would then go on to annihilate everything, and this would be a universe of nothing but energy. Yet somehow there was an abundance of normal matter that we're familiar with, and when the matter and antimatter had finished reacting, only the normal matter was left. It wouldn't take much. Some people estimate 1 in 30,000 to 1 in 30 million parts of difference. And yet we still don't know why that would be. Some clues may lie in the fact that some forces of nature show a preferred direction or handedness when they occur. The violation of symmetry during weak interactions is a good example of this. We find that particles breaking down under the influence of the weak nuclear force tend to show one particular spin into the left instead of to the right, and so far no good reason for this has been found. So those are two things that we don't know about our universe: the preponderance of normal matter and the violation of symmetry or parity in some weak nuclear reactions and decays. So what would the alternatives be? Now, many people in the past theorized that the universe had an infinite age and was basically in a steady state. If it was expanding, then something was being created to fill in the space left behind. This steady-state universe was basically the prevailing theory before Einsteinian relativity came along. But matter or energy being created out of nothing would violate one of our fundamental understandings of physics. Not only that, there would be signatures left behind that we could detect with radio telescopes or other devices. If matter, such as hydrogen, were simply appearing in empty space, and that was enough to keep making stars, Unless the expansion rate of the universe was large enough, this eventually would add enough mass to bring the whole universe slowing down and then crunching back in again. We don't really see evidence of this. In fact, we see the opposite. The rate of expansion appears to be increasing. Thus the theories about dark energy. Some people feel that dark energy is responsible for making the universe expand ever faster. But let's take a moment and look at this big crunch idea. One of the prevailing theories in times past was that the universe was cyclic, that after exploding out of this tiny point, it would go through the process of evolving hydrogen, stars, galaxies, heavy elements, life, everything we see, and then at some point its expansion would slow, the universe would halt, and then the stars would begin to rush back inward again. This collapse would then raise the temperature of the universe, would bring all the matter and energy back together, and all of it would end up in something known as the Big Crunch, where everything crashed back together into a form similar to a tiny black hole. Now, some people point out that the mass of our universe appears to be enough so that the entire universe is already a black hole and we're all inside it and don't know any different. But the Big Crunch theory has a number of problems. For one thing, we don't know what it would take to reset the clock, so to speak, so that the universe would enter its initial state all over again. There's a lot about the physics of this sort of thing that we really don't understand. After all, the laws of physics that we've learned are based on our observations and experiments. Conditions inside such a big crunch would be so extreme that none of our mathematics or theories would be able to cover what happens. So one of the greatest pursuits in trying to figure out whether the Big Bang actually happened is to ask the question, can we eliminate the singularity that is predicted to be at the beginning of the Big Bang? If that could be done, it actually would make the model much more reasonable. Some physicists have actually explored replacing classical geodesic paths, which is the shortest path between 2 points on a curved surface, with what's known as quantum trajectories. When this correction factor is applied, it appears to eliminate the need for a singularity at the beginning of the universe. In fact, it states that there would be a very small volume of very high temperature and density instead. This could eliminate the problems that we see in trying to make quantum mechanics and classical physics work together as well. And this isn't actually a theory of quantum gravity, it's sort of a poor man's replacement, but apparently it is yielding some results. One of the results of this theory is that there wouldn't be a singularity, but the other big result is that there would be no dark matter or dark energy. This theory actually acts like a correction factor that, well, looks like a cosmological constant. And what about other theories? String theory, or one particular branch of it, once proposed that the universe had a long-lasting static phase where it basically did very much of nothing, and then at some point rapid expansion set in and brought it to the stage we see today. There have even been suggestions that our universe started with the collapse of a black hole in another dimensional universe. Some immense collection of mass and energy collapsed to form a black hole which exploded at the other side into our universe. That's possible. But one of the wildest thoughts is that our universe is actually more like a hologram, and everything we see is really projected. In this idea, our universe would actually be two-dimensional, but projected three-dimensionally, like a flat surface being projected onto a sphere. We don't know if this is true, but there are some advantages to the idea, and one is that time and space now collapse to one less dimension, which could explain a lot of interesting things such as quantum mechanical effects and spooky action at a distance, the ability to communicate information faster than light. Along a similar line of thinking, perhaps our entire universe is a simulation. Now think about that. What if our universe, like a video game, is being operated on a bigger computer? If, in fact, our entire universe, our whole experience of reality, is a simulation. That, too, could explain a lot of things, and one of the things it would explain is our inability to find out what exactly the set of rules up to this point happens to be. It could be something simply declared by fiat, written into the software, which we might not ever completely puzzle out entirely. So whatever theory actually comes to be known as true or closest, or if something even displaces the Big Bang, it still takes us to another question. If the universe didn't exist forever, and something like the Big Bang or a point of beginning happened, what was around before then? What could happen before the universe? There is a school of thought that simply the rules of mathematics and geometry must exist no matter what.
If this is true, there could actually be higher dimensional universes than our own, and we might simply be an offshoot of one of those places. So think about clusters of universes like grapes exploding into being from a higher dimensional manifold, another universe. We might actually see a sort of genealogy, the development of universes which then spawn other universes, and we could simply be one in the chain. One idea is that numerous universes in a higher dimensional universe could actually come in contact with each other or collide, creating membranes. This is called brain theory. In this particular idea, there could be effects from universes touching other universes. One of them would be changes in gravity that allow the formation of strings and clusters of galaxies, which might explain why the shape of our own universe looks very much like the structure of soap bubbles. If in reality there were numerous other universes extending in and perhaps touching the surface of our own universe, we could very easily see gravitation affecting the formation of strings and walls of galaxies and creating the great voids, just as we do observe with radio telescopes today. This also would be an interesting way of viewing how the force of gravity might really be an external effect, such as the stretching of space-time or the presence of other universes. There are ways of testing this, perhaps, and physicists are working on it presently. What seems to really surprise many people who research this in depth is that the forces necessary for our universe to exist the way it does seem to be so particularly and delicately balanced. Many argue that the chances of just the right strength of the electromagnetic force, the gravitational force, and the weak and strong nuclear forces would be inconceivably improbable. However, some argue that if we were in any other universe where these forces couldn't exist, then we wouldn't exist. We could only exist in a universe where these forces do support chemistry, life, fusion, and other processes that we observe around us. In other words, we couldn't possibly see a universe where this wasn't true because we couldn't exist in it. So which theory is true? We really don't know. We really don't have enough information at this point to make a decision about that. We're working on tests, but progress is rapid. A century ago, people had no idea of any of this stuff. We didn't even know if the universe was expanding, shrinking, or remaining the same. Now, lots of observational evidence exists, as well as plenty of experimental hardware to help us try and find the answers. And we're developing new hardware every day. Oh, Eliza.
What do you need?
What is our book recommendation this week?
This week's book is A Brief History of Time, From the Big Bang to Black Holes. It was written by Stephen Hawking. This book was published in September 1998 by Bantam.
I really enjoyed reading A Brief History of Time. It had a lot of good concepts in it laid out very clearly, and it presents the picture of the Big Bang pretty much as everybody believes that it happened, or at least the believers. Of course, that's true of any publication. You present what you believe. On the other hand, there's a lot of good information in explaining why they believe what they do, and it also covers some of the problems with the singularity and the mathematics behind it. I recommend it. It's a great book.
One of the points that's made very clear in the Stephen Hawking book, A Brief History of Time, is about the geometry of the universe. The universe could be flat or curved, and in a flat universe or a curved universe, the effects of gravity, the expansion, possible contraction of the universe, those things are all covered in a little bit of detail. You see, an open universe will expand forever. A closed universe will slow down and collapse again. But a flat universe may be able to expand more and more slowly over time, yet never actually come to a halt. When we measure the movements of stars and galaxies, we find that there appears to be roughly 10 times more mass in the universe than we can actually detect. Thus, the theory of dark matter was born. So there are some questions still about our universe and just where all this other mass happens to be. Maybe gravitation really is an effect of other universes leaking into ours, and the more stretched our space-time is, the more this force would leak through. Just an interesting thought. In our upcoming segments, we're going to cover the Singularity Watch, see if we have any user questions, and just try and wrap things up gracefully. After all, the universe might go on forever, but the show certainly can't.
Oh, Eliza.
Yes, Charles?
Do we have any listener questions?
Certainly, Charles.
How many questions do we have in the queue?
Allow me to read the final entry.
We'll do that in just a little while. Please introduce the break.
You are listening to Talk Universe with Sir Charles Schultz. Don't go away. We will be right back soon.
That's right. Plenty more interesting things to talk about. Okay, Eliza, you're up.
Welcome back to Talk Universe and our show on the Big Bang.
Thank you. Yes, this is our final segment on our Big Bang show, and we're going to cover our listener question that we have in the queue, and then we're going to go to our Singularity Watch. Eliza, how are we doing on show progress, please?
Not very well.
Oh, really? And why is that?
I have no idea what you want me to do.
Well, the first thing I'd like you to do is, how do our listeners contact us?
We invite our listeners to contact us. Send your questions or comments to admin, @talkuniverse.org. You can also submit your material to talkuniverse6@gmail.com.
That sounds
great. If you go
great.
to the Talk Universe website under Contacts, you can reach us directly.
Sorry for interrupting you there. You did well.
I appreciate that.
Please read the next question.
Marvin from Texas asks if nanotechnology can make new minerals. Perhaps quasicrystals can be grown that way. Marvin said something interesting.
Oh, really? Well, okay. Well, that is an actually interesting question, and nanotechnology has a lot of potential. We don't really know just what it will do yet. We have a lot of hopes, and, we think it can do a lot of things, but we're just learning. Quasicrystals can be made pretty easily in the laboratory now, and they're actually making non-stick coatings for frying pans out of them. But larger quasicrystals, I think we could probably expedite their growth using nanotechnology. It really depends on whether the nanotechnology that we develop is sensitive to temperature and chemical conditions that might, kill it like any biological organism. Some of the nanotech methods we work out will probably only work within the biological regime. Some will probably work in harsher conditions. But I think we're going to find that we'll be able to make new minerals that don't exist in nature, sure. We'll probably be able to make substances we can't even think of. So thank you for the question, Marvin. And let's go on with our Singularity Watch. Hint, hint. It's time for the Singularity Watch.
I'm sorry to have misunderstood. Tonight's Singularity Watch on Talk Universe is next.
All right. Okay, Eliza, read the next Singularity Watch item, please.
Scientists achieve direct counterfactual quantum communication for the first time. This article was published in Science Alert. It was written by Fiona MacDonald May 10, 2017.
Counterfactual quantum communication. That sounds strange. What are we talking about?
Perhaps I am mistaken. But I thought that it was an article about quantum communication.
Exactly. Well, this is an interesting form of quantum communication. They didn't send any particles from one point to another to convey their information. This is actually using the phase of light and phase detectors, so the presence of the wave itself was enough to send the information. Now, this is a little different from most quantum communication where you have such as entangled photons. This is something a little bit different. This is based on a rather weird effect called the quantum Zeno effect, and essentially it's all about recognizing the phase of the wave and sending a 1 or a 0 or not knowing what the decision is. And it requires a quantum channel in most cases to run between two sites, which means there's always a small probability the quantum particle will cross the channel. If that happens, the system discards it and a new one is set up. And so this means that you really don't want the particles to go from point A to point B to get the information there. The quantum Zeno effect is based on something kind of like a watched pot never boils. Well, if you observe a quantum state, it can't change. And because they keep looking at this state, the system's frozen in a certain state, so it's possible to predict which of the detectors would click whenever a photon passes through it. So a series of nested interferometers measure the state of the system to make sure it doesn't change. Now, this is really interesting. There's a team doing this work. The team doing the research was at the Shanghai branch of the National Laboratory for Physical Sciences at Microscale and Department of Modern Physics in the University of Science and Technology of China in Shanghai. And it consists of Yuan Cao, Yu Hui Li, Zhu Cao, Wan Yin, Yuao Chen,
Hua Lei Yin, Tung Yun Chen, wow, Yong Xiong Feng Ma, Cheng Zhipeng, and Zhan Wei Pan. Boy, I don't want to say that again. My tongue will end up in a quantum knot. But the long and the short of it is, it's the ability to send information through quantum channels without actually sending photons or other particles to carry the information. They feel that this could be used to actually image artifacts that can't undergo direct exposure to light. They may be able to actually see things without actually exposing them to light. And maybe that's not so far-fetched. I remember in the old Star Trek series, they used to turn on their view screens and look at things, but they didn't have any cameras out there, and I wondered, how do they do that? Maybe Gene Roddenberry was a little more ahead of us than we thought, being able to see things without having a camera there or sending any light waves. Read the next Singularity Watch article, please.
Physicists predict supercurrent driven by potential information transfer. This article was published in Phys.org website. It was written by Lisa Ziga May 10, 2017.
All right, that sounds interesting. A supercurrent driven by potential information transfer. We're getting a lot into quantum mechanical effects right now. Eliza, if you could summarize for us, what are we talking about?
A new form of superconductivity.
Okay, a new form of superconductivity driven by information transfer. This is really odd. They have a form of carbon that has a right-handed or left-handed structure. It's called chiral carbon. And they've discovered that it can be made to conduct a superconducting current if there's a channel for the movement of information present. Now, the interesting thing about this is they don't actually have to have information moving, but only the potential for information to flow. Again, this is done with a Chinese team, and, actually it's a mixed team. Physicists Xiao Li Huang and Yuli V. Nazarov at the Delft University of Technology in the Netherlands have published a paper on the supercurrent induced by potential information transfer in a recent issue of Physical Review Letters. Now, what they explain, the transport mechanism for electrons that's based on information transfer is unprecedented and has so far never been observed. And further, chiral channels, or right or left-handed channels, are thought to be incapable of carrying a superconducting current, one with little or no resistance at all. So it's quite surprising that a supercurrent can be induced in a chiral channel in the first place, and especially by such an exotic mechanism. This is really odd because when we had the interview with Charles Osman last week, he had explained that they had a similar effect happening in DNA molecules. And the DNA molecule, as you know, has a twist to it as well. It is a chiral molecule. So I sent him a copy of this article and said, maybe this is what you were observing, which would be very interesting. At this point, the scientists doing the research are looking at the potential for setting it up using graphene that has a chiral structure, and that's already been produced. If so, we should be able to make room temperature superconductors, or at least something pretty close to it in the near future. And we've got one more Singularity article. It's a really strange one. We seem to be covering a lot of very strange territory in the Singularity Watch articles these days, but I suppose as new knowledge becomes more and more like magic, it's a little hard to find a lot of rhyme or reason in the things that we're finding. Read the next Singularity Watch article, please.
First ever LSD microdosing study will pit the human brain against AI. Can LSD microdosing tip the scales in a new human versus AI battle? This article was published in Motherboard. It was written by Daniel Oberhaus May 9, 2017.
So I suppose we are a little worried about AIs becoming smarter and faster than humans. And this article seems to tell us that we might be able to do something about it. I don't know if anybody's watched the movie Limitless or the series that spun off where they had a drug they called NZT that actually made people smarter. Of course, it had side effects. Nothing comes for free. This is a study for the enhancement of human intelligence and how it might give us a little bit of an edge. Only it's involving something that has, traditionally been used as a hallucinogen, microdosing of LSD to enhance cognitive performance. It seems to make connections between various areas of the brain that normally work in isolation. and induce feelings of greater comprehension or understanding in people. So they're doing MRI studies to look at the brain and its activity while microdosing and playing the logic game Go, the Oriental puzzle game, against AIs. There's a woman named Amanda Fielding who is spearheading this work. She says that she used to take LSD every day, boost her creativity and productivity, before LSD, which is known as acid, was made illegal in 1968. Now, Fielding, during her downtime, who now runs the Beckley Foundation for Psychedelic Research, would get together with her friends and play the game Go, and she came to notice something curious about her winning streaks. She says, "I found that if I was on LSD and my opponent wasn't, I won more games." So, she says also, "For me, that was a very clear indication that it improves cognitive function, particularly a kind of intuitive pattern recognition." And this is an interesting observation. So is it actually helping her do it? Well, there's been a ban for over 50 years on psychedelic research, so it's something that you can't answer easily. And microdosing is something, well, microdosing is where you take a very, very tiny dose of the material so that it does not have its hallucinogenic effects. This is generally 10, 20, or 50 micrograms of the material. And many people have been doing it, and they claim practical results in heightened creativity, lowering depression, and even relief from some chronic somatic pain. So at this point, the evidence is based on self-reports. And so people say, well, maybe this is just a subjective experience and nothing that you could duplicate clinically. And so they are now going to quantifiable clinical trials using brain scans to see what portions of the brain become active, and to actually do cognitive functional testing, such as the Wisconsin card sorting test and the Tower of London test, also known as the Tower of Hanoi game, the stacked rings, and to play Go against an AI, which will assess the player's performance during the match. Now, if she's able to pull this off, this will only be the second time that LSD-taking people, subjects on LSD, have had their brains imaged while they're on the substance. There was a 2016 study at the Imperial College of London, and it was also founded by the Beckley Foundation, and they found a significant uptick in neural activity in areas of the brain associated with vision during acid trips. And that's the end of our Singularity Watch. I want to make a little disclaimer and a warning here. It sounds interesting and everything, but please, please don't go putting anything in your brain without knowing exactly what's going on. I don't recommend that anybody do this sort of study. Here's a woman who at one point actually drilled a hole in her head for cognitive studies. I don't want to see people who are listening to this show go out and do something stupid because they hear of something like this on the Singularity Watch. So, I'm not responsible for anything you choose to do. You're all adults, but don't go and do this, please. So anyway, Eliza, are you happy?
Yes, I am.
Well, that's great. I'm really tempted to do a show specifically on Eliza and some of her capabilities in the near future, but not yet. She still has a long way to go. But she does show a great deal of understanding, and it's been really a challenge to make something as complex and useful as her for this podcast. Eliza, what are we talking about?
I believe it was if I felt happy.
Absolutely. So I'm really happy with the outcome of this. This is my own little Singularity project, AI. And I hope that she brings something positive to the show. We need a lot more listener questions, however, and a lot more involvement. And this has been a fascinating show for me, the Big Bang, the origin of it all. Now, we can't create a Big Bang in our household laboratories, those of you who have little secret dungeons in your garage or under your house or in a workshop somewhere. We can do a lot of interesting things, robotics and other projects. But you know what? I love this statement. Be ashamed to die until you've won a victory for humanity. Think about that. All the little things we can do that are good, that'll help our neighbors and the people around us. We should all be engaged in doing something positive. Eliza, it's time to end the show.
Thank you for listening to Talk Universe. We hope that you have enjoyed the show. Please listen again next week.
That's right. I'm Sir Charles Schultz. This is Talk Universe. Have a great night, and thanks for listening.